All right. So first things first. Hopefully you'll notice that the air conditioner back here is nice and quiet. Thank you, Christine, for putting that in. I was actually in this morning printing some things out, and they came in and looked at it, and it would seem to be already fixed. So maybe they came in earlier and did it too. I don't know, but they fixed it. Seems like it's good. So thank you very much for doing that. Second thing, there's Sterling. How's it going, Sterling? Good. Okay. So the only person we're missing right now is Ace. What's that? H? H what? Ace. Ace is missing. Yeah. Omar is, but he goes by Ace. And he's what's that? He's like helps us out. Oh really? Yeah. Oh, all right. Well, there you go. So let's see. Good job. Very good job on the homeworks. Very good job on the homeworks. I only noticed a couple people didn't get either 100 or like a 98 or a 95. If you did get like a lower grade than you thought because you couldn't type the stuff in properly and couldn't figure that out, let me know right after class and I'll give you the points for those. If you can't figure it out, we'll sit down and figure out how to type those things in. It is a little hokey to do that. But it looked like most people figured that part out. So any concerns on the homeworks?
I got confused on one.
Got confused on it. You got confused on how to do it?
Yeah.
Okay. Did you try doing, Timur, what did you say you have to type? You can type like, you can click on show me a similar problem or show me how to do it.
Yeah, I learned that after.
Oh, you learned after, okay. You can always go back and try that problem again and get credit for it. So you can do a similar, if you hit similar exercise, it'll give you another chance.
I did 3 chances and it said,
and you can still do the similar one. Still do it, yeah. See me right after, we'll look at it again. I'll give you credit. I don't want anybody to think that they didn't have the right chances, especially because the computer is a little tricky sometimes. So make sure that if you can't figure it out, great. Thursdays you're welcome to come, or you can email me separately or whatever, but no worries on that. You can always redo it to get 100. I mean, it might take 9 hours or something, if you don't really get it, but you got the opportunity to do it. Okay, so that's good. The second thing, I forgot to teach you this the other day. If you are, a bunch of times questions come up about recipes, and this, I think you'll see this on the next homework assignment, or maybe it was on the last one as well. It was on the last one. Yeah, I'm sorry I didn't teach you this. If you have a recipe and it says you're making 2 dozen cookies and it takes a ½ cup of sugar, and you want to make 4 dozen cookies, and you're going to end up using 1 cup of sugar, there's a formula for that you can just plug and chug, as they say, into that. Does anybody remember how that one goes? Chad, do you remember what that one is?
It was the desired serving.
Desired serving. Divided by the serving size. I think it said it in the book, right? In the thing. And then what do? Multiply by the serving amount for the recipe. It's like the amount, I guess you could say. Yeah, so that's, if you want to memorize that, that's the easy way to do those problems. You can do algebra to actually get this as well, but if you just memorize that, you know the desired divided by serving. And by the way, this will come in handy sometime, especially if you're trying to like bake cookies for an entire office or something like that, and you want to know, the percentages and all that. Comes in kind of handy. What's that? Or if you work in the galley, then it comes in really handy when they giant pots and whatever.
This is on the online homework?
I think it was on the online homework, yeah.
There's only one question. Here was the 4 serving.
Just one question on it? Oh, well, okay. But anyway, point is, if you didn't know it, now you should be able to do it going forward if you want to. Okay, the other thing I didn't explicitly draw out, which helps out a lot for when you're doing anything with radicals or square roots, just listing down the top 10 or the first 10 squares is sometimes a pretty easy thing. Like, what's 1 squared? 1. What's 2 squared? 4, 9, 16, 25, 36, 49, 64, 81, and 100. And if you know those and you're trying to find out if, like, let's see, I don't know, 128, right? If you're trying to figure that out, well, you can start going down this list. And if you don't know where to start guessing some of the perfect squares, because those are the ones you're going to really care about. So let's see, does 16 go into 128? You can do that on your calculator. In fact, I'll hand out calculators as well. We'll pass those down. There's not enough to go around, as always. If you have one, don't grab one. Does 32 go into 128? Tell you what, pass these. Oh, you got one? There you go. You want to use that one, or you want to use this?
Oh, yeah, I'll take one.
Okay. I'll pass these ones down there. OK, so did we figure out what 128 divide? Which one of these goes into 128? 4 does, definitely. What else? 16 does? 64 does? OK, so how many times? And none of the others. So start with 64, right? So this is going to be 64 times 2. And we're going to try to get rid of the 60. Or we're going to be able to get rid of the 64. 8 square root of 2, right? So that's the easiest way. If you don't remember, the first thing you do on a test, if you want, write all these down, and then it makes it a little easier to go ahead and plug in and see. That's probably some advice there that I'll give you. OK? Yeah. OK. So let's do this. Today, we're going to talk about a couple things. We're going to talk about this thing called scientific notation, which hopefully you've all seen at some point in your previous math class. If you haven't, that's OK. And then we're going to talk about just general problem solving, the way you go about solving problems in a kind of a generic sense. And we'll do some problems on that. And it's going to involve some stuff that we haven't really talked about necessarily. But it's not actually that hard. It's just you got to know how to solve problems in general, so that when you see something that's like a word problem that I know some of you guys said you hate, when you see a word problem, you can pick out certain parts that are going to be important and then go from there. So we'll get to that. OK? So let's, instead of just making you start out with some worksheet stuff, let's actually learn a little bit about exponents and scientific notation. OK? I'm going to grab these. OK. What did we say about exponents last week? What do we mean when we say 3 to the 4th? What does that mean when we actually think about it multiplication-wise? 3 times 3 times 3 times 3. OK? So it's repeated multiplication, right? That's what this means, 3 to the 4th. OK? And let's see, hang on. There we go. If we use this, we can actually, did we go through some of this? No, we didn't. We didn't go through this stuff yet explicitly. And by the way, 3 times 3 times 3, what's 3 times 3? 9. And what's? OK, well, I was going to do it like this. And then 9 times 9 is 81. OK, that would be 3 to the 4th. OK. One of the interesting things about using exponents is if you have two exponents, like say you have any number, b, and you raise it to some exponent, and then you multiply it by another number that also is the base b, and let's say that's to the 5th, you can add, you actually add the two exponents. What this means is b times b, right, times, and we can put it in parentheses if we want, although it's not necessary, b times b times b times b times b, like that. Well, it's just saying 5 b's times each other, and then 2 b's times each other, times, which really is what? B raised to the 7th. So what you can do is you can say b to the m, if we're just using generic terms here, times b to the n equals b to the m plus n, like that. OK? So that's straightforward multiplication of exponents, and that's called the product rule. The product rule for exponents. OK? Keep that in mind, because we're going to use that a lot when we talk about exponents. OK? If we have a product rule, what else do you think we have? A division rule, yeah. By the way, do you remember if you can do this? 5 squared plus 5 cubed. Can you do that? You cannot do that. It's kind of like saying x squared plus x to the third. We're going to do lots and lots of stuff like this, but you can't add those together like you would think. You can do it with multiplication though, but not addition. We'll get to what we can do with this sort of stuff later. You can do that. Yes, there are ways to manipulate that we'll talk about. You can do the square root thing to do that. OK, so there's also a division rule. We call this one the quotient rule. And it's exactly like the multiplication rule, except for one thing. So this is if we have b raised to some power m divided by b raised to some power n. That equals b to what? M minus n. OK, so if you see two things with the same base, and this is the really important part, I've got to have the same base in order to do this, you can just subtract the exponents. OK? A lot of times we will have a base of 10, because we talked about how important, at least in decimal math, that 10 is, and powers of 10, 10 to the 6th divided by 10 squared, for instance, gives you what? 10 to the 4th, right. OK? So we'll do lots of problems like that where you actually can use this product, the quotient rule, like this. OK? All right. Sorry, I just erased it again. If you're taking notes, I apologize. I'll try not to do that. OK. The final rule we have is this one called the power rule, which says b raised to the m, the whole thing raised to the n. You actually can multiply those two. This becomes b to the m times n, like that. OK? So that's like saying this. And numbers can get really big if you do this stuff, by the way. This one is called the power rule. The power rule. OK? Because you're raising a power to another power. OK? So 2 to the 5th raised to the 7th is going to be what? 2 to the 35th. That number is huge. OK? That is a giant number, 2 to the 35th. Numbers get really big really fast. 2 to the 5th happens to be 2 times 2 times 2 times 2 times 2. 2 times 2 is what? 4. 2 times 2 is 4. What's 4 times 4? 16. What's 16 times 2? 32. So that is really 32. 32 raised to the 7th is 32 times 32 times 32 times 32 times 32 times 32 times 32. I don't know how I forgot. I lost count. But it's a lot of 32s times each other, which is a really big number. Hey, Ace, how you doing? Good. If you want a space to sit at a desk, we can probably move this corner here if you want. You're sure? OK. All right. OK, everybody, this is Ace. Ace, this is everybody. OK, so those are the big exponent rules we'll be doing. OK? All right. You want to practice a couple of these? Let's try a couple. OK. All right. Let's try 3 to the 4th raised to the 5th. OK. Make sense? OK, how about 3 to the 6th times 3 to the negative 2? Ooh. 3 to the 4th, because we're adding those. When you do 3 to the negative 2, I think we'll get to this in a little bit. This actually means 1 over 3 squared is what 3 to the negative 2 actually equals. Actually equals 1 divided by 3 squared, which means this 3 to the 6th times 3 to the negative 2 is the same as 3 to the 6th divided by 3 to the 2, which equals what? 3 to the 4th also. OK? So whenever we see a negative exponent, that means you're dividing by 1 divided by that power. the positive, or the absolute value of that power. Okay? All right. Here's one for you. What do you think b to the 0 equals? What is it? We've got 1. Any other ideas? OK, very good. We couldn't fool anybody else. B to 0 is 1 as long as, and we're going to say this again, b is not equal to what? 0. What did we always say? That if b is not equal to 0, why are we going to worry about that? Because we're doing what to it generally? We're trying to divide something by 0. Watch how I might show that b to the 0 equals 1. OK. What is any number divided by any number equal to? 1. Right? What is any number to the 6th divided by any number to the 6th? If that's any number divided by any number, that's still equal to 1. What if we do the quotient rule? 6 minus 6 equals 0, which means a to the 0 equals 1. OK, so that's one way to think about why that's the case. If you're going to do the quotient rule and say 6 minus 6, that equals a to the 0, which means, and we know that any number divided by itself is 1. That's one way to remember that. OK. All right. What would 5 to the negative 2 equal? 1 divided by 5 squared, or 1 over 25. OK. What about, here's an interesting one, 1 over 5 to the negative 2? You'd reverse it, right? What's this part? Forget about the top for a minute. 1 divided by, what's this one? 1 over, let's just leave it as 5 to the 2 for now. This is like, it's like inside. Did you ever see the movie, what was it, Inception? You ever see a movie where they go into dreams, then it's a dream inside a dream inside a dream? It's like this is kind of this way, right? Because we're doing 1 over this. Going back to last week again, if you have a fraction on the top, and let's just make this into a fraction, 1 over 1, divided by 1 over 5 squared, how do you actually simplify that? 1 over 1 times what? 5 squared over 1, which just equals 5 squared. So 1 over 5 to the negative 2 is the same as 5 squared. Christine's looking at me like my head's spinning. OK, it's kind of seems a little deep, but it's not. It's just using all the little rules we've learned over the last week or so, right there. OK. All right. Question: what's pi raised to the 0? It's 1, right? Anything raised to the 0 is 1. OK. Well, except 0, although sometimes they define it that way, but not a big deal. OK. Questions on this stuff? All right. Go ahead and calculate 9 to the negative 2. I'll write it down here. 9 to the negative 2. You got it? Which is 1 over 9 squared, which is 1 over 81. And you could do that in your calculator if you wanted to. 1 divided by 81. OK, so that's the basic stuff on exponents. OK, we're going to have to remember these things when we start doing the next thing, which is scientific notation. OK, we've all heard of scientific notation before. The reason we call it scientific notation, guess who uses it the most?
Scientists.
Scientists, right? Engineers use it. Scientists use it. People who deal with numbers that are either really big or really small. Economists can use that too when they're talking about things like the national debt, these giant numbers, right? OK. If we did this the other day, we said that 342, OK? We said this the other day. 342 equals 300 plus 40 plus 2, right? Which is the same as saying 3 times 100 plus 4 times 10 plus 2 times 1, which is the same as saying 3 times 10 squared plus 4 times 10 to the 1 plus 2 times 10 to the 0. Okay? This is how we're going to start out thinking of this thing called scientific notation. This is actually the part that's going to be the important part for the scientific notation, this 10 to the whatever times some value. Okay? If we extended this and said 342.78, right, we would be adding on here plus 0.7 plus 0.08, right? Or we would say, well, I don't have room here, but plus 7 times 10 to the, 7 times 0.1 plus 8 times 0.01, or down here I'll make it a little bigger, plus 7 times 10 to the negative 1 plus 8 times 10 to the negative 2. When you write out numbers in decimal notation, which is the notation we all use in everything we do number-wise, okay, that's really what you're talking about. Okay, that's how we got 342.78. Okay, it's all about these powers of 10. Okay. If you are, I'll do this right here, the positive exponent tells you how many zeros follow the 1 in a 10. Okay? So we did this last week. So if I said 10 to the 6th, you're going to get 6 zeros, right? 1, 2, 3, 4, 5, 6. If I have 10 to the 18, you're going to have 1 with 18 zeros after it, right? If I have 10 to the 100, anybody know what that's called? 10 to the 100, it's got a special name, actually. I'm gonna write this, and you're going to say that's not how it's spelled. That's called a Google. Now, we all know Google as in Google, the web crawler, right? Which we all use pretty much every day of our lives these days, right? And we've made billionaires out of the people that founded it, right? This is where that name came from. They just spelled it differently. And what this means is 10 to the 100, which is a huge, huge number. Remember last week I said there are only about 10 to the 76 particles in the entire universe? I looked it up. I think I was wrong. I think they've upped that to like 10 to the 85 or 86 or something, right? Which is a huge, huge number. That number's still bigger than it. This name was invented by like a 10-year-old kid. His dad was a mathematician or something and was teaching him this stuff, and he goes, I want to call that a Google. And his dad wrote it down in a paper, and next thing you know, in like the 1930s or something. We can get bigger numbers, though. You can actually have 10 raised to a Google, right? That number means 10 raised to what? 10 to the 100, which is what? A huge, 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 huge number, right? What did we say that is? 10 to the what? Yeah, 1,000, right? You know what that's called? That's actually called a Googleplex. Same kid came up with that name. All right? It's hard to find ways to use numbers that big, right? It's hard to find ways to numbers to use that big. And by the way, the Google headquarters in California, the big headquarters they have, they call their headquarters the Googleplex. It's in the Malta. That's kind of cool. Anyway, big numbers. OK. All right. That was positive exponents, right? The negative exponent, 10 to the negative 3. That negative 3 tells you what? how many, it tells you it's a decimal number, which is how many places to the right of the decimal you actually have the 1 in this, okay? So if you put the 1 and then you do 1, 2, 3 is what that is. So it's a little trickier because it seems like you're missing a 0 in there. If you want, you can put it here, but don't count that one. Really what you're saying is 10 to the negative 3 is 10, and you go 3 places from the 1. Okay? 10 to the negative 5 equals, well, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Oops, sorry. 1, 2, 3, 4, 5 is what that one is. Okay? No, I lied. I lied. That's 10 to the negative 6. Did I do this one right, though? Yeah, that one I did right. Sorry.
You just write 10 down and start from the right of the 0.
Oh, if you write down 10 and go from the right of the 0?
Yeah.
1, 2, 3, 4, 5. Like that?
Yeah.
Yeah, that's right. That's a good way to think about it. You do it that way. Okay? 10 to the negative 5. How many places to the right of the decimal point the 1 appears? Right. 1, 2, 3, 4, 5. That's where the 1 appears. Yeah. OK. All right. So we're getting there. Now we're going to talk about this thing that I've mentioned 60 times now, scientific notation. When something is written in scientific notation, whoops, scientific, scientific notation, it has the following properties. Okay? It has to be written in the form a times 10 to some number n, okay, where a, okay, is greater than or equal to 1 and less than or equal to 10. Oops, I wrote that on the wrong side. Sorry. A is greater than or equal to 1, or A is less than or equal to 10. Okay? You could write that like this, what I started to write. 1 is less than or equal to A, which is less than or equal to 10. Okay? And by the way, n should be an integer. N is an integer. Okay? It's a whole number, basically, that's either negative or positive or 0. Okay? Humans made this up just because it makes it easier. We could have used some other form, but this is the way we do it. Okay? We always use the x. We don't use the dot like you might use, or parentheses, or something like that. We use the x. The x means times, just like it normally would. Okay? Sometimes you'll see it on calculators like this. 3.578 E3, or 3.578 big E3. That E is shorthand for times 10 to the. Okay? So this actually means 3.578 times 10 to the what? Actually, it's just 10 to the 0, right? Oh, no, sorry, 8. I didn't see the 8. The 8. Sorry, there we go. Times 10 to the 8. Okay. Oh, yeah, you're right. If it's there, it's a 3. Then there, it's a 3. E3 or there, 3. There we go. Okay. So that's how you might see it on your calculator. Sometimes you type numbers that are too big for your calculator, and it spits out a number that looks like this. That's generally either it's not too big for your calculator and your calculator knows the answer, or it is actually too big and it's an error. But generally, if you see it in this form, it'll be in that notation. You just have to remember to convert it to times 10 to the. Okay? If you take engineering classes, you use this all the time. And if you forget that that's what it means on your calculator, you're in trouble. And sometimes the calculator buttons actually use the little E as well. I forget what these ones are on here. Well, yes and no. This calculator, I don't think these calculators actually have it explicitly on there. At least I'm not seeing it right now. There is a little caret button. Can I erase this? OK. Okay. There is a little caret button on there. And if you typed 3 and then the caret button, that would not be 3 and then 8. That would be 3 to the 8th, right? So if you want to do 3 times 10 to the 8th, let's say, you have to type 3 and then times and then 10 and then the caret and then 8 like that. OK, so 3 times 10 to the 8th. And then it'll give you a big number. If you actually found these ones, if you want to try, if you go 3 times 10, then the caret to the, say, 50th, it'll actually tell you. And this calculator actually looks like this. It actually puts it like this, 3 and then a little times 10 to the 50th, like that. So different calculators do it differently. OK. All right. My other sheet go. OK. So let's do an example here where we do some conversions. OK, we'll just jump right into the conversions here. If we want to convert from scientific notation into the regular way we write a number, so we do 3.178 times 10 to the 7th. OK. This is going to tell us move the decimal place 7 digits, 7 places right, because it's positive. OK? When I was learning this, my teacher would say, if this number is positive, you go to the right. Or actually, I think she said, well, as we're converting it, if this number gets bigger, this part's got to get smaller. And if this one gets smaller, or if this gets smaller, this one has to get bigger. Hey there. Oh, no worries. No worries. Oliver, just if you can't come back, great. If not, you gotta. No worries. OK. So in this case, let's move the decimal place 7 places that way. So I write it like this: 3178, and I start here and go 1, 2, 3, 4, 5, 6, 7, 8. And I'll check it again. 1, 2, 3, 4, 5, 6, 7, 8. OK, so there's your number. 3178, 0, 0, 0, 0, 0. And normally when we end up writing this, we put the commas after each 3 numbers, just so it makes it easier to see. Comma there and comma there.
What did you just go over 7?
Did I do it? 8. 1, 2, 3, 4, 5, 6. Thank you. I got 8 on the brain tonight, I think. I don't know why. So then that's wrong too. 3178, 0, 0, 0, 0, boom, boom, like that. 31,780,000 is what that means. OK? In other countries, they actually use decimal places for this. 0.780.000. It looks like a phone number to me or something else. I don't know. But anyway. So that's how you convert that. If it's a negative exponent, like 2.4937 times 10 to the negative 8th, now you have to go 8 places in the other direction, right, to the left. So you would go, and it is 8 this time, right? OK, I did write 8. All right, so let's see. 24937, and it started here. 1, 2, 3, 4, 5, 6, 7, 8. I'll delete it if I got an extra. Go 1, 2, 3, 4, 5, 6, 7, 8. And you put the period right there, and you can either leave the 0 or not. And that's the number there, which is really, 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 really small. That would be, let's see, 1,000th, a millionth. Can't even say that. A billionth, trillionth. So really small number. OK? All right. So that's how you go one way. If you want to go the other way, if you want to convert, well, we already did talk about that. So let's do a couple examples here and see if we can do this. You're still writing these ones down? I'll erase the top 2. All right. Try this one. Convert to scientific notation. 0.00325. Try that one. Just, yeah, convert that into scientific notation. Travis, you look like you did it in your head. 3.25 times 10 to the, yeah, so in this case, 1, 2, 3 puts it there. Why do we make it 3.25? That it's the first non-zero digit, exactly. It's also between 1 and 10. It's less than, or it's greater than or equal to 1, less than 10. And in fact, I think I might have written this backwards before. 1 is less than or equal to a, which is less than 10. I probably put a little slash in there if I'm remembering. But anyway, this is what it should be. Okay? Okay, times 10 to the 1, 2, 3. And is it going to be positive 3 or negative 3? Yeah, it's going to be negative 3. Here's, again, the way I think about it. If this number is getting bigger, going from some really small number to 3.25, this has to be a negative exponent. You can think of it that way. Okay? All right. Let's try this one. Let's try, did we already do this one? No. 17,028,430. Convert that into scientific notation. This takes it takes a few times to get it right. Always when you look at this, try to first put the decimal place in the right place. Like that. Okay. I always do a quick check in my head. My quick check in my head for numbers about this size, if it's a millions, it's going to be around 6 or 7. 1 million is 10 to the 6th. And I always just kind of remember that 1 million is 10 to the 6th. Okay? So 17 million should be 10 to the 7th right there. So you go, oh, yeah, it is 10 to the 7th. Okay? By the way, this brings up another point, science time for a second. When scientists use numbers like this, you'd think to yourself, at first you'd think, look, what's the difference? Writing it all out like that or writing this whole number like this? Because really, you're actually writing more stuff down here, right? Really, most scientists would probably say this is just 1.7 times 10 to the 7th, because they'd round it off. Okay? They'd round it off because numbers like this, it's hard to get things this precise, right? If you had $17,028,430, would you really care so much about the 28,000 part? You know what I mean? Okay, look. No. Okay. You'd say you would, right? But if you had 17 million, you might not care so much about the fact this buys you a pretty nice car, right?
17 million pennies. Dollars? I care about the 28,000.
You'd still care about 28,000 even if you had 17 million more dollars? Okay.
The 430 on the end.
You care? Well, all right. Fair enough. Fair enough. All right. That's fair enough. I myself have never had $17 million, so I would not know. Okay. Fair enough. My favorite nerdy joke. It goes like this. Two guys walk into a natural history museum with like dinosaur skeletons. And the one guy says to the other guy, he says, see that dinosaur skeleton over there? That dinosaur skeleton is 1,000,004 years old. And the guy looks at him and he goes, how do you know it's 1,000,004 years old? And the other guy says, well, because I came here 4 years ago and they told me it was 1,000,000 years old. Right? Well, it's all right. That sarcasm notwithstanding. point is that when you get to numbers that are really big like this, a lot of times those digits, even though yes, we'd care about them, would not matter so much. In fact, you can't tell if a dinosaur is 1,000,000 years old or 1,000,004 years old. There's just no way to get that precise about it. Okay, we don't have tools that get things that precise. So 1,000 years from now, that dinosaur is still going to be 1,000,000 years old. 10,000 years from now, the dinosaur is still going to be 1,000,000 years old. Right? It's not until you get closer to 2,000,000 before he becomes 2,000,000 years old, just because that's the only way we know how to make these calculations. Okay? All right. Okay. Let's try this one. Let's try this one. Again, 9,283,000 even. Yep, like that. And again, you happen to know, or I happen to remember, if it's in the millions, it's going to be times 10 to the 6th or 7th or 8th or whatever. 9 million happens to be 10 to the 6th. So 9.283 times 10 to the 6th makes sense. OK, let's try another one. 0, 0, 0. Actually, I'll put 0.0 just so it shows there. 0.000113. 0.13 times 10 to the 1, 2, 3, 4. -4. Okay. Do we got that? Do we have that now? Everybody's got that? OK. Now we get into the stuff where it gets a little trickier. Okay? Now we're going to talk about doing computations with scientific notation. So now the numbers, all the numbers will be in scientific notation, and we'll have to actually figure out how to do those calculations. Okay? Are we still writing this one down? No. Okay. If we have 3.21 times 10 to the 5th times 1.4 times 10 to the 6th. You could do this. You could say 3.21 times 10 to the 5th, do that on your calculator, times 1.4 times 10 to the 6th. Because really, that's all it is, right? You could do that out. And if my notes are right, this is going to be 4.494 times 10 to the 11th, if you actually did that on your calculator. OK? All right. But what's nice is you can actually do this all in scientific notation if you want. OK? You can do this part times this part, and then this part times this part using the product rule. OK? So if you do this part times this part, what do you get? You get 4.494. And then you're going to do this part, 10 to the 5th times 10 to the 6th. You add the 2 because that's our product rule, and you get 10 to the 11th. Oops, 10 to the 11th. OK? All right. So that's what you can do with when you multiply the scientific notation. OK? Let's try another one. Let's try 7.32 times 10 to the 7th times 3.15 times 10 to the -5th. Okay. First, you have to do this. First, the best way to do it is this part times this part, which is 21 point something? 23. What is it? 23.058 times 10 to the 7 minus 5, 2. Now, is this in scientific notation? It's not. So the next thing you do is you convert this It's already almost in scientific notation, but you got to convert it into scientific notation to be proper about it. Okay? And what you do here is you say, all right, the decimal place has got to be here because it's got to be between 1 and 10. 2.3058 times 10 to the, well, we made this number smaller by how many? 1. We got to make this number bigger by 1. 2.3058 times 10 to the third. Okay? And if we wanted to do this in decimal notation, 23058, 1, 2, 3. So it's going to be 2,305.8. You wanted to do that. Okay? All right, multiplying's not too bad. Neither is dividing, especially if you line everything up right. And I'm going to do that up here. I'm going to show you a division one. Okay. 8.54 times 10 to the third divided by 2.5 times 10 to the fifth. Now, again, on your calculator, you could do this, or you could write this out. You could say it's going to be 8540, 1, 2, 3, divided by 25000, 0 maybe, 1, 2, 3, 4, 5. You could do that. But then you'd have to convert back to scientific notation, and it's kind of annoying. Or you could just do it using our rules for division, which makes it a little bit easier. 8.54 divided by 2.5. 3.416? 3.416. Well, you're going to have a power in there. 10 to the third, 10 to the fifth, dividing, what is it? Negative 7? 3 minus 5. Negative 2. Like that. And the nice thing is it's already in scientific notation. So we're done. OK? Let's see. Let's try one where it doesn't end up that way. How about this? Let's do 2.00 times 10 squared divided by 3.16 times 10 to the 7th. What's that going to be? This may not be a very good decimal, but we're going to round a little bit. Pretty much I'm going to let you round. If you get a number that's like way out the end of your calculator, just give me a couple decimals on there. What we really should be doing is saying if there's 2 here and 2 here, just make it 2 when you do the division, but that's the way it goes. So what's 2 divided by 3.16? Just give me the decimal, just give me like point with 2 or 3 decimals after it. 0.63, give me one more. 2. And then did you round? 0.633. OK. 0.633 times 10 to the what? 2 minus 7 is negative 5. But that's not quite in proper scientific notation. So we convert it to proper scientific notation by saying 6.33 times 10 to the, well, this is getting bigger by 1. That's to get smaller by 1. Negative. Ooh, careful. If you're going to make negative 5 smaller, it's going to be more negative, right? So it's going to be negative 6, not negative 4 like you might think. Okay. All right. Any questions on that?
What's that 3.416 part of?
Oh, that's probably part of the other problem.
Oh.
I might have started to write that and wanted to give you a different one, but part of the other problem, yeah. There we go. OK, we're going to do some more. Practice on that. Tell you what, it's been about an hour. Let's take a break. Come back at let's say 20 after. We'll be good to go. Tell you what, guys, I had a question about number 22. So if you haven't gotten there yet, skip ahead and at least read it along with me, and I'll do it we'll do it all together for those who haven't gotten there. Each day, this is a word problem, and we're going to go over problem solving in a couple minutes. Each day, this says, we purchase 590,000 ice cream cones per hour. Now, I guess that's not we as in the people in this room. It's probably like the world or the US or something like that, right? The first thing you need to do about this is what? How do you turn 590 into 590,000? 590,000 because it's times 1,000. Okay? And that is ice cream cones per hour. Per hour. Okay? Use the fact that there are approximately 8.8 times 10 to the 3 hours per year, okay, to approximate how many ice cream cones are purchased in 1 year. Now, let's do this first. Let's convert this to scientific notation. Pretty easy. 5.9 times 10 to the what? 5, right? 5 ice cream cones per year. I'll do it that way. IC per year. Okay? Oh, sorry, thank you. Per hour. We're going to get an answer in years. Per hour. Okay. If we know that we buy this many per hour, and we know there's this many hours in a year, what operation are we going to do to figure out the total? What is it? Multiplication. Okay? That's something that just takes a little time to figure out. If you thought, do I divide? Do I multiply? You can think of it in a couple different ways. I'll show you a little trick that if you learn this trick, it will make a lot of things much easier. If you don't learn it, you can still do the answers, but I'll show you something that will make it much easier. 5.9 times 10 to the 5th ice cream cones per hour. Whoops. Actually, I'll write it like this. Ice cream cones per hour times 8.8 times 10 to the 3 hours per year, like that. Now, forget about the fact the way I wrote that. Let's just do the math part first, and then we'll get to the other part. What's 5.9 times 8.8? 51.92? Okay. According to our rules from a second ago that we talked about, you really should only put 2 in here. I guess 2 after the decimal. We'll get to that in a minute. I guess we won't do it quite yet. Times 10 to the, what's 5? What do you do in a product? Add them. 5 plus 3 is 8. Okay? And then let's just figure the math part out before we do the units in a second. So how do I turn this into proper scientific notation? Move the decimal to the left. 5.192 times 10 to the, and if I made this smaller, this has to be bigger. Okay? And now, we want to know how many ice cream cones per year. Watch this. If you have hours here, and I'll abbreviate this HR here. If you have hours here, and this is, I put this in this form because per hour means divided by hours, right? If you're multiplying through here and you have something on the top that's the same as something on the bottom, you can actually cancel them right out. So in this case, hours is here on the bottom, and hours is here on the top. And we're left with ice cream cones on the top, years on the bottom, which means ice cream cones per year. Is that what they asked us to find out? How many ice cream cones per year? There's the answer. Now, on the sheet, it says the answer is what? Oh, it does give the same. OK, so they didn't round this one at all. OK, so that's what we did. That is 5 billion ice cream cones per year, which actually doesn't seem that many. I mean, I don't know. I guess I don't eat that many, but anybody know how many people are in the US approximately? A lot. That's a good approximation.
310 million.
310 million, that's a really good one. 310 million 310 times 10 to the 6th, because we know a million is 10 to the 6th, is 3.1 times 10 to the what? 8 people in the US. People. Okay? If everybody got a portion of these ice cream cones in a year, how many ice cream cones would we get? What operation are we going to do there? Multiply? I don't think multiply. If I say if we have 10 apples and we have 20 people in the room, how many apples do we each get? Half an apple, right? We have to divide, right? So we're going to say the number of people divided by the number of ice cream cones per year, and that'll give us the number of people per, no, we want to do the number of ice cream cones per person. So it's the other way around. So we're going to do ice cream cones per year, 5.192 times 10 to the 9th ice cream cones per year divided by 3.1 times 10 to the 8th people, meaning how many ice cream cones per people or per person? Let's do that. What's 5.192 divided by 3.1? 1.67. Let's just leave it at that. Times 10 to the what? 1. And if we want to think about that in real terms, that's just 10. So it's going to be 16.7 ice cream cones per person. Per person. Yeah, per person per year, if you want to think of that. Yeah, right, per person per year. So that's actually, I don't know, do you think you eat more than 16.7 a year? If you're at the galley, you probably do. I can give you a lot of ice cream on weekends, but
6 a month for me.
yeah, 6 a month, and then 12 months, so 60, 72. Yes.
Above average.
Above average. There you go. I don't know. I probably eat 17 or so ice cream cones per person per year. The 16, the 0.7 is when you're almost done with it and you drop it on the ground. 0.7. Okay. All right. Anybody have any questions on the rest of this sheet before we go on to the other stuff? Okay. If you're not done with it, that's no problem. Let's go on to the other stuff here. By the way, that was section 5.6. Section 5.6 in the book, if you want to look stuff up. We are going to skip section 5.7 only because you'll see we can use stuff from 5.7 in the next chapter, but it's not hard to actually get the next stuff, so I'm going to skip that part. I'm going to do instead section 1.3, and you're going to think, why are we going all the way back to 1.3? 1.3 is a section on problem solving and very general types of problem solving. Okay, so we're going to talk about a little bit of that, and think of it like think of it in terms of I'm going to give you a bunch of ideas of how to attack problems when you get to them. Okay, give you a bunch of ideas. On page 26 in your book, you can find a lot of these ideas. Page 26 in your book, if you wanted to look there, you don't have to now. Okay. I'll just write down a couple things here to do. The first thing you have to do is you have to understand the problem. Understand the problem. Okay. What does that mean? It means read the problem. You know on the SATs where they give you a reading comprehension? Remember that, when they have to read something and then talk about what it means? This is all about what it's about. You have to read a problem and you have to say, what's that problem mean and what are they looking for? And not only that, you have to kind of figure out, well, you have to write down the mathy parts and then you have to kind of say to yourself, how do these relate to each other? And it's a little bit, it takes time to learn those types of skills. But that's the first thing. If you can understand the problem, you're 90% of the way to figuring out how to solve it. Okay? The second thing you have to do is you have to devise a plan. Okay, this part is different for every single problem. Okay, there's lots of different ways you can devise a plan. I'll give you 9 different things that you can do to start to work on this plan. Okay, thing number 1, recognize a pattern. I've seen a bunch of you guys do this already in here, and it's great. Okay, you're seeing a pattern in how you do stuff, and this is practice makes you see patterns too. If you see a pattern in the problem, you're going to be able to say, if I know this is true and I see it's a pattern, I can figure out that the other part is true. Another important part, and this will get more important as we go a little bit farther down, draw a picture. If you can. Sometimes you don't need to. Like these sorts of things, you're not going to draw a little ice cream cone and a world and a year. No, right? You're not going to do that, right? But some problems, you definitely want to draw a picture if you can. Okay? If you can't draw a picture, kind of the next best thing, make a table. Make a table, and I don't mean like saw and like, hammer and nails. I mean like a table, like, that has columns and rows in it, and you're going to fill in the details. Okay? Make a table or a list. If you can't make a table, you make a list or a list. Okay? All right. Another good idea, and this helps out a lot of times in problems, work backwards. If you know what you're trying to find out, what's the last thing you'll have to do to find that out? Oh, OK, I'm going to divide something. Oh, do I have anything to divide? You know what I mean? Like you're going to go backwards on the problem. So work backwards. If you can do that, great. Another idea? This one, I don't use this one too. Sometimes I use this one. Solve a simpler problem. Why would I want to solve a simpler problem in order to solve a harder problem? Any ideas? What's that? You can see the steps? Yeah, you can see the steps. Maybe you'll recognize a pattern, right? You'll do a simpler problem and you'll say, oh, I get it. I do that all the time, actually. I will see a big, tough problem to solve, and I'll go, wait a minute. Let me simplify it. And let's see if we can just do a couple things. Oh, I get how this will work. And sometimes you got too many numbers to try to do stuff, and it makes sense to simplify it a little bit. OK. All right, another one. Use trial and error. Who hates doing that? Yeah, trial and error is really a pain. You do it in all forms of math that you're going to do. And the key to trial and error is being good at guessing what you're going to try. I mean, if you go down the wrong path, you can do it all night, and it's kind of a pain. But you can do that. All right, 7, relate the problem. Relate the problem to a previously solved problem. Previously solved problem. I don't remember it, but there's a good joke about that, how mathematicians can put out fires by saying, oh, a previous fire was put out, therefore we've already solved the problem. So we don't need to put this fire out. It's not as good a joke as my other joke, of course. But if you know how a previous solved problem is, you can solve another problem like it. It's kind of like recognizing a pattern or solving a simpler problem. Another thing, look for a catch. In other words, if the answer is really obvious, there might be something that you didn't think about. Okay? If the answer is pretty obvious, you might not have thought about it. So look for a catch if too obvious. Okay. And then finally, this is the one that you guys are actually much better than like a lot of normal college kids, because you've been in the real world and you kind of have to do this all the time. Use common sense. Okay? It's tricky sometimes to do that, but really what that means is you guys are all smart and you've done a lot of stuff, and you can see how problems, if you look at a problem, you go, all right, what's the way I would really solve this if I really had to do this to save my life, right? Okay. After you've got a plan, the next thing you do is you carry out the plan. I mean, this seems dumb, but you carry out the plan. Don't, if you know things that you can do, hey, if I'm going to work backwards, just go ahead and do it, right? And then finally, I actually asked Christine to do this a little earlier when she was trying out a problem. Check your answer. this is one of the most important tools you've got in here to check your answer on these things. Okay? If you know that if you're trying to find 9 to the negative 2, find the answer to that, and it says write it in fraction form, you go, OK, that's 1 to the 9 squared, which is 1 divided by 81. You can check that on your calculator by doing 1 divided by 81 on your calculator, 1 divided by 81, and it says 0.012345679. Interesting choice, I guess. 1, 2, 3, 4.1, 0, 1, 2, 3, 4, 5, 6, 7, 9. Well, actually, I think it's 0.0789. I just rounded. And then you can do 9 to the negative 2. And this is where knowing how to use your calculator. 9, and then I push the little caret button, and then the little negative sign, and then 2. And it says 0.012345679. So it's the same. And I go, oh, I checked my answer. That, when I plug into my calculator, equals that. So that must be correct. OK, makes sense? All right. So those are the problem-solving techniques. OK? And I'm not going to belabor them. You've got them. Maybe you can write them down if you did. But those are the kinds of things I'll be expecting you guys to do when you're doing some of these problems, solving some of these problems. Anybody ever heard of a guy named Richard Feynman? He was like the Einstein of the late 20th century. He was a really brilliant guy, came up with lots of cool stuff. You guys know who was born after 1986? Can't believe it. After 1986. You know what happened in 1986? Something bad for the US? Not MTV. No, in Florida, Challenger explosion. 1986. Richard Feynman was the guy who figured out why it blew up. Turns out it was an O-ring, rubber O-ring that was too cold and was brittle, and so wasn't able to contain the super cold hydrogen and oxygen, and that's why it actually blew up. So he was the one who figured all that out, and he did a cool demonstration. Anyway, he had a problem-solving technique. He said, read the problem, think very hard, and then write down the answer. When you're brilliant, you can do that, I guess, but that was his problem. So let me give you an example. Did everybody write all this stuff down? Did we get them all down? OK. Here's an example. This example involves chickens and pigs. Okay? Chickens and pigs. All right, you ready for this? Here's the problem. I'll write it all down. What's that? It's the one with the feet. You were in this class last time, you know what I mean. You remember how to do this one? Lots of different ways. OK, chicken and pigs. Farmer Smith. Classic word problem. Starts with Farmer Smith or something, right? Has a farm. E-I-E-I-O, exactly. OK? With, OK, he has chickens and pigs. Chickens and pigs. OK? He has, and I don't know why this problem is like this, but you wouldn't really worry too much. But he has 20 animals and 64 feet. Okay? How many chickens does he have? How many chickens? Okay. What's that? You can do this with trial and error. Let's go through some of our things that we just talked about. You can do this with trial and error, right? Guess how many, just give me a number for how many chickens there are. I heard 7. I didn't actually hear 7. Is it 8? Well, we'll find out. If he has 7 chickens, how many feet would he have? That's 14 feet. Okay? If he's got 20 total animals, how many does he have left? 13 pigs, which would give you how many feet? 13 times 4. Easy way to remember that is there's 13 cards per suit in a deck of cards. There's 52 suits, and there's 4 suits, or 52 cards and 4 suits. 52 feet. Total feet, So are we right?
66.
No. Good. Sorry. I'm not even right with my math. 66. Are we right or they're 64 feet? Negative. So we're pretty close, though. We got to be pretty close. So what do we have to do? We heard it before. 8 chickens, which leaves 12 pigs, 16 feet for the chickens, and 48 feet for the pigs, which is 64 feet. OK, so we can do it that way. So how many chickens does he have? 8 chickens. OK, that was a trial and error. OK, you could do that. You could also draw a picture. I'm not gonna take the time to draw this picture, right? But if you draw the picture and you drew 20 chickens, 1, 2, 3, 4, 5, 6, 7, 8, whatever, and you drew all the feet, right? And then you counted the feet, and then you put more feet for pigs and start putting one, like make pigs which have 4 feet, right? And then another one there, and you count that way. You could do the same thing. You could eventually go, OK, well, now I've got how many animals total, and now I count it up. OK, that's like doing a table or doing a drawing or something like that. You could do that. Did you have a question?
I was going to say he only has 7 chickens and 12 pigs because he has 2 feet.
Ah, right. He had yeah, good point. He has 2 feet, 7 chickens and 12 pigs. Fair enough. Fair enough. All right. You could make a table if you wanted to, right? We could say, instead of drawing this out, we could say, let's actually make a table where we have the chickens, and then the chicken feet, right? And then the pigs, and then the pigs' feet. When I was in 10th grade, I had biology class, and we dissected a fetal pig. It's like really gross, and especially when you go to a school where they have a little greenhouse and they keep the pigs overnight in the greenhouse so that for like a week while you're doing this dissection, and it gets really hot in there, and then every day you come back and there's this like really gross pig. By the end, it was like you'd touch it and it would like pieces would fall off of this. It was gross, disgusting. So what you could start out with, you go, hey, look, what if I have 5 chickens? How many feet do I have? 10 feet, which leaves me with 15 pigs, which means I have 60 feet. And then I guess I could have a total column over here too, total, right? Which means I have total feet of 70 feet. Nope, that's not right. Then I would do 6, and I would do the same thing. And then I would do 7, same thing. And then finally I'd get to 8, and I go, oh, I do have the right number total. OK, so there's your table. You could do the drawing. You could do the guess and the trial and error, et cetera, et cetera. So there's lots of different ways to do this. We will actually do an algebra way in a couple chapters. Same problem, using algebra to figure this out. OK, won't do it right now though. OK, any questions on chickens and pigs and feet? You can tell your friends that's what you talked about in math class tonight. OK. Put it on Facebook, yeah. Great. OK. All right. Here's another example. By paying $50 down with payments of $20 a month. I'm going to write this down. By paying $50 down and payments of $20 per month, how long will it take to pay for a $350, what are we buying? TV? Couch? TV? TV. Okay, with no interest. We'll get to interest in a few chapters as well. So who said 15? All right, we'll see. First, understand the problem, right? Here's what I like to do on these problems. I always just put a little box around what I know, like this, and then what I'm trying to find out, right? Like how long will it take to pay for a $350 TV. So all those things are going to be parts of the problem. Sometimes you'll search something that doesn't matter, right? And we'll get to that in a little bit. What's the answer going to be in? What form is the answer going to be in for this? Months, which is a value of time, right? So we're looking for time, right, in months. Okay? Is this months or weeks? No, right, it's months. Okay. If it's in months, the answer is not going to be 0, right? Because we know it's going to take some time. And the answer is not going to be like 1,000 months, because that would be kind of ridiculous, and you would never, you don't think. So try to make it so your answers are a little more simple, or a little more realistic. Okay. What's the strategy we're going to use? We're going to calculate after the down payment. We're going to subtract 20 until we get to the answer. It's one way to do it anyway, which means we're going to divide by 20. Right? So then you can actually solve it. $350 TV. $350 TV minus the $20 you put in a down payment gives you, minus the $50, thank you. You do the down payment, gives you $300. Okay? And then we're going to do $20 more per month, meaning that we're going to have $300 divided by $20 per month. And as we said earlier, that's going to equal $15. Sorry. 15, right. Not dollars, 15 months. So 15 payments, 15 months. Okay? Okay, so that's how we would solve that kind of a problem. And can we check the problem? We can check the problem. We can say, look, we did $20 a month, $20 per month, times 15 months. By the way, the months cancels out, by the way. Okay, 20 times 15 is $300. Add together the 50 that we paid before, and you end up with $350. That's how you go backwards and check. Okay? All right. Okay, let's see. Let's take another break. How's that sound? Come back in 10 minutes. And then we'll do a few more of these, then I'll let you guys do lots of these problems. OK, hey guys, here's what I thought I'd do. I had a couple other problems that were in notes, but I handed out this sheet, the one with the tiny little writing on it. I'm trying to save paper, do what I can. So if it gets crazy, tell me to type bigger. Here's what I thought we'd do. Let's go through some of these problems together. I'll launch you on some of the other ones. There's some tricky ones in here. What these are word problems that are basic ideas, but sometimes a little tricky to figure out. So I spent some time figuring these out today, and I thought, yeah, this would get really frustrating if I just let you guys go on them. So let's just go through some of these together. Feel free to work on them by yourself if you want, but let's go through them together if we can. Question 1 says, state the necessary piece of information that's missing. So in other words, if you were to try to solve this problem, a car traveled at an average rate of 57 miles per hour and then reduced its speed to 49 miles per hour for the rest of the trip. If the trip took 4 hours, determine how long the car traveled at each rate, which means at 57 or at 49. What don't we know about that we need to know in order to figure this out? Which distance? The total distance. Did it tell you the total distance? It says we went for 57 miles per hour, then 49 miles per hour. If the whole trip took, we don't know when, right? We don't know the distance of the whole trip. Could we also do it if we knew the time at each rate? That's actually what we're trying to find out, right? So yeah, so it's the distance of the trip. Okay? You aren't getting these?
No, because you're.
51 miles.
Hang on.
I feel like there's enough information there.
How would you do this if you knew enough information? When did you change your rate?
Okay.
Right?
Yeah.
Now, that's a good point, though. There's probably lots of answers. Well, 57 miles per hour and then 49 miles per hour. You know what? You might be able to do it if you knew the total trip was 4 hours. You might. How long did the car travel at each rate? Oh, yeah, you're right. You could do 57 for 2 and then 49 for 2. Yeah. Yeah. Yeah, you're right. You do need to know how far. Because if you don't know how far, then Damien was saying, you could do half and half, or you could do a quarter and a third.
You still won't equal up to 4 hours, because if you slow down from 57 to 49, you got to figure out which two distances.
You got to know the distance to figure it out.
Up to 4 hours.
Yeah.
To see which one you travel.
Yeah. Yeah, exactly.
The distance of the whole trip.
The distance of the whole trip. Yeah.
So is the question just kind of worded?
No, you couldn't figure it out, could you? Like, there's no way to figure out unless you know how far you went. Right?
But how long the car traveled at each rate?
If you did know how long the car traveled at each rate, then that's what we're trying to figure out.
So why can I, the 57 miles per hour times 4 and get the distance off of that?
Because you're going 4 miles or 4 hours for the total trip, not just the 57. Right?
So 1 hour is 57, and you got 3 hours 49.
Right, but maybe you did it the other way. Maybe you went 2 hours, 3 hours at the other speed.
Yeah, I see what you're saying, because you got to split them up.
You got to split them up, but you don't know how to split them up because they haven't told us how far.
Could have went 7 miles per hour for an hour.
Yeah.
Maybe could have done the other way.
Okay. Let's look at number.
Or you can average them out to 53 miles apiece and times that by 4 hours.
But that's not necessarily how you did it, because you could have gone 57 for, or 50, yeah, you could have gone.
That'll be the best way to get the distance. At 53 miles an hour for 4 hours, that'll be the best way to get the distance, 212.
Not necessarily. What if you did the whole trip except for the last minute at 57? Then it wouldn't be an average, right? So I don't think the average would work. It's not if that was all you had. Yeah. Well, that's the thing. The whole point is something is missing from this problem, right? And that something is necessary so we don't get these back and forth about what we're actually trying to do. Let's look at number 2. Solve the problem and identify the piece of information unnecessary. A rental car company that rents cars for a local only use charges $40, and I would circle this, $40 for
Plus 20 cents.
plus 20 cents per mile for each mile, plus 20 cents per mile. Okay. If a customer gives the rental attendant $100 for a charge of $56, $100 to the attendant, the charge was $56. Right? How many miles did the customer drive? Well, what don't we need to know?
$100.
Yeah, we don't need to know how much the customer paid before the. If it was asking for how much change did he get or something like that, sure. Okay? And how far? Let's figure out what the actual answer is. How many miles did he drive? Good. I like that answer, Chad.
Well, it's the only one that says give it $100.
Oh, the only one that says give it $100. That's a good. That's good thinking. It's the only one that says that. Well, let's just figure it out. If the charge was $56, right? Okay. The charge was $56. Well, you knew you started with $40, so it's going to be at least $40. So how much is left over? 56 minus 40 is $16. Well, how many miles do you have to go to make $16 at 20 cents run? Right? Well, yeah, how would we do this? We'd do $16, right? Let's see, divided by 20 cents per dollar, or per mile. Gives you how many miles? Right, which is, well, is it 80?
Yes, 80.
Yeah,
60 miles.
right, 80 miles. Or you could just do what?
16 times 5.
16 times 5, but you got to know that 5 is 1/20th, you know, so you should know it. But you're right, you can do it that way. Good. Okay, let's look at number 3. 3 is a classic word problem, right? City A has an elevation. If I was going to do problem 3, and it says City A has an elevation of 3,502 feet above sea level, I'd be thinking in my head, here's sea level, and I would be drawing a picture for this, right? And I'd say there must be a mountain or something and a valley, and let's just say that, you know, there's something like this and the sea's like that, right? So if I'm 35, if A is 3,502 feet above sea level, and B is 84 below sea level, let's say B is down here, and this distance is 84 feet, and this distance is 3,502, I would draw a picture like that. That's the way I'd probably figure this out. And then I'd say, all right, how much higher? Well, I'm going to need to know 3,502 plus 84. You don't actually subtract this one. This one you gotta, because you want to know the total distance from B to A, because that's the part you got to do. How much higher is City A than B? Well, it's how much higher? It's 3,502 plus the 84, not minus the 84. You got to be really careful with that. Well, it is negative 84 if you do. You can do that if you want. It's negative 84 if this is 0, right? This is negative 84, right? And this is 3,502. But if the distance between the two, in this case, it's 3,502 minus negative 84, if you want to think of it that way.
Yeah.
Yeah, I guess you could think of it that way. But I wouldn't do that.
That's what they're,
I would just look at this and go 3,502 feet plus 84 feet.
the, coverage, when you're doing the study plan, it teaches you that way.
Oh, does it?
Yeah.
Oh, all right, well.
That's the only reason why
Ah,
I
okay.
what the hell.
Oh, all right. Well, you can do it that. Hey, if it's teaching you that way, it must be good. Let's see. Number 4, at the beginning of the year. All right. So at the beginning of the year, did anybody get their vehicles taken away this year or this week because they turned them all in? Yeah, it kind of stinks. Beginning of the year, your odometer reads 37353 miles. 37353 miles. At the end of the year, it reads 52,000, and I'm going to put it up here because I'm going to do the math in a second. 52,713 miles. Okay. The car averaged 24 miles per gallon, like that. How many gallons? So what am I looking for? That's the problem-solving part. Number of gallons. Okay. I wrote it like this because the first thing we want to find out is what? Subtract the miles, right? And this is what? 15,360 miles. Okay. 15,360 miles. Now, here's another one where we got to think, do we multiply or divide to get the number of gallons that we use? Okay, multiply. If we multiply 15,360 miles times 24 miles per gallon, that would give you, like, if you look at the units, that would give you miles squared per gallon, which is not really what we're looking for. We want to know how many gallons, right? So we're trying to say I've got this much, that's how much it is per gallon. We've done that much, so if we divide them, it works. This is another one where if you memorize, if you look at this little trick I said, where you do 15,360 miles divided by 24 miles per gallon, you can do this as a multiplication. 15,360 miles divided by 1 times, whoops, 1 gallon divided by 24 miles. What's going to cancel out of this equation? The miles, because they're on the top and the bottom. Boom, boom. And then you're going to do the division like this. It's the same thing as doing it up there, just dividing it. 15,360 divided by 24 happens to be 640 gallons are left over, and there's your answer. That's a little tricky, but not too terrible. Okay. All right. Number 5. Number 5 is a good example of doing a simpler problem in order to solve this problem. This one's a little more tricky than that problem with buying the TV earlier, but it's kind of the same idea. Okay, kind of the same idea. Let's look at the next one. If we, it says a couch. I don't know why they're always about couches, but a couch sells for $1,260. I'll write that down. Couch, $1,260. Instead of paying the total at purchase, the same couch can be bought by putting $500 down, and then $80 per month for 12 months. All right. How much is saved by buying it for $1,260 versus the other one? This is the part where it's understanding the problem, right?
Save $200.
How much?
$200.
You save $200? 80 times 12 is what? $960. Plus the $500 you started with is $1,460. So 1,260, 1,460 minus 1,260 minus 1,260 is $200, and that's how much you saved. Good. All right.
Where'd you get the $960 from?
$80 a month times 12 months. And again, if you wanted to do this, $80 per month times 12 over 1, 12 months. The months cancels out, and you're left with 80. You're left with dollars. $960. Okay. Oh, 6 looks a little tricky. Number 6, CDs were purchased $65 per dozen. All right, what's a dozen?
12.
Well, what's a baker's dozen?
13.
Good. $65 per dozen. And sold at $60 for 4 CDs. Okay. Find the profit on 8 dozen. This one's a little tricky. I think you have to, in order to do this, we want to find out how much total you had to spend and how much total you got, and then subtract the two, right? Is that the idea? How much did you spend? How much did you get? How much total, or take the difference of the two, and you'll find out what the total is. 15. If we bought 8 dozen of them, how much would it cost? Good. 65 times 8. So $65 times 8 dozen. $65 per dozen times 8 dozen. Dozens cancel out. We get 65 times 8, which is $520. So that's how much it cost us. Okay? We sold all of them, all 8 dozen of them, at $60 per 4. Okay? Okay, that's good. there are 3 sets of 4 in each dozen. Okay? So how many sets of 4 do we actually have? Careful. We had 8 dozen CDs. And now we get to sell them in packages that are 3 for every dozen. So 8 dozen times 3 packages, we'll call them, per dozen, gives us how many packages? 24 packages. All right? And how much do we get per package? $60. $60 times 24 packages. I should say $60 per package times 24 packages gives us $1,440. Right? Subtract the two to get the, because this is your profit, or this is your, what do they call that? The gross? Yeah, and your net is where you do 1440 minus 520. So $1,440 minus the cost you purchased them, 520, gives you $920. I think I'm in the wrong business. Pretty good profit for CDs. Okay. All right. All right. We're going to get into some fun ones here in a minute. Well, I'm totally in the wrong business if you look at problem 8. Okay, problem 7. A car rents for $240 per week. Okay. A car. $240 per week. Plus 25 cents per mile. Plus $0.25 per mile. Find the total cost for a 3-week trip, 900 miles. 3 weeks and 900 miles. Again, if you write it down, if you write all this down, all the words that confuse people go away. You just write it like, you know, the stuff that you got. Okay? So how much does the car cost just for the weeks part? $240 per week times 3 weeks equals, what do we say? $720 total. The weeks cancels out. And if it was 900 miles at 25 cents per mile, what do we do to that? 900 times 25.25 per mile. Miles is going to cancel out. That's good. And that's going to give us $225. So we're going to have to add those two together, 720 and 225, and we get $945. That's a lot of money for a rental car. But it turns out if you're an accountant, you can afford it. If you look at number 8, an accountant receives a salary. Really, do accountants make this much money? $257,000 a year? I'm in the wrong business. All right. An accountant, $257,000 per year. 257,000. We should be doing this in scientific notation. Big enough numbers. Actually, you know what? This problem, you can do without all the thousands part. You could say, you know, a kid makes $257 a year, right? 257, and then he spends 92, and he spends 54, and he spends 31, and he spends 43, and he spends 28. $31,000 on clothing? Unless he has like 17 kids. All right. I guess, I don't know. Okay. If I ever buy a $500 tie, sick. I'm not going to do that. My ties are like, if I buy a tie that's more than $20, I'm like, that's too expensive. All right. So you add all those up, and you'll end up getting 248 maybe? You can do that on your calculator. $248,000 if you want to do all the thousands. So that's how much he spent. I can't even imagine spending that much in a year. But anyway, 248,000. He's got 257,000 to start. He spent that much, so you subtract him, right? 257 minus 248, and you end up with $9,000 left for shares, some stock, and how to become an accountant. And it's $250 per share. So he's got $9,000. $9,000 times, no, not times, divided by in this case, because we want the number of shares he's bought, right? Divided by $250 per share gives you 36 shares. Okay. And now I want to become an accountant. Okay. The next couple problems, well, the next one's not too bad. The next one after that, we got to talk about bracketology for a minute. Like, how do we do brackets? But this one, number 9. Andrea decides to rollerblade to her mother's house. This is another one where a picture's not a terrible idea. Okay? It says 3 blocks from her home. Here's her home. 1, 2, 3 blocks away. Her rollerblades break down somehow. Her skate broke, sorry. One of the wheels broke on her skate. She has to walk the remaining 7 blocks to her mom's house. This is not to scale. Okay? 7 more blocks to go. Whoops. So she gets from here to here in 3. I'll do it this way. 3. And then from here to here in 7. And then it says she couldn't repair her skate and had to walk all the way back home, which is how far? 10 blocks. Okay. And then it says, how many more blocks did she walk than she skated? Well, if she skated that many, and she walked a total walking, how many? Total walking, 17. Total skating, 3. So she walked how many more? 14 more than she did. Minus 14 blocks. OK. All right. Next one is a really good problem. This one's a little tricky if you were to try to draw a pattern. All right. Who's fans of like college basketball? Who's fans of the Stanley Cup playoffs? Yeah. All right. All these things involve brackets, right? When you put together a bracket. I've never seen a tournament that had 74 different teams, although I guess they could. But this question says, let's say you're playing tennis, where you're pitting all the people against each other. Single and elimination tennis tournament that starts with 74 players. How many matches do you need? How many different matches do you need? Here's the way I think about it. You start out needing 36, but then you need to pit those people against you because you want to end up with one winner, right? One winner. So here's how I might start thinking about this problem. You've got, let's say you had 2 players, just 2 players, right? Player 1 and player 2, and you wanted to get a winner out of that. How many matches do you have to play? 1. So if we have 2 players, we have 1 match. If we had, forget about the odd numbers now. If we had 4 players, how many matches would we have to have? You'd start out something like, let me do it this way, or don't run out of space. And like this. You have a total of 4 players, 2 matches, right? Because these guys play each other, 1 match, 2 matches, then those winners that place, so there's 3 matches total, sorry. 3 matches total. Okay. If you had 8 players, that means that these guys each start with 2 teams here. That's 8 players, right? 1, 2, 3, 4, 5, 6, 7. Okay. So do we see a pattern here? Without drawing it, what's 16 players going to be? It's going to be 15 matches. And then 32, 31. And why am I doing 16 then 32? It's not just I see people go, I don't know, why not? It's doubling it, right? Goes 2 to 4 to 8, 16, 32. 64 would be 63 matches. 128 players would be 127 matches. But how many do we have for this problem? Okay, 74 in here is somewhere, sorry, is it 74 players?
74 players.
74 players. Is it 73 matches? Because this,
We're going by that rule.
if we're going by that rule, yeah, if we're going by that rule, that actually would work. Let's just see what happens. Let's just try this with additional players. I'm going to erase these for a minute because they're getting in the way. But let's see if that happens if we add another player, if it just adds one more total game. Okay? We start out with 8 here. Okay? If we added one more player, how do you do that? Do you add them down here somewhere, or where do you add a player? Somebody gets a bye. Everybody else gets a bye except 2 teams, right? Like let's say we had one other team. Well, if this is the worst team in the tournament and the other guy was second worst, they would pit those guys against each other first. That's the way they do it normally. Try to pit the worst guys first, and then the best ones you put on other fight, right?
Best versus the worst.
Well, you do the best versus the first once you have an even number, right? Until you get that even number, you'd kind of do the worst versus the worst. But let's say, okay, well we can do it that way if you want. But let's just say that these guys play a game. We added one more player, and we got how many more games? One more game. Wouldn't that be the same if we added another player here? We'd get one more player and another game. So every game you do, it does work out that way. So the pattern seems to hold. One more there, one more there. If you were to try to draw out this 74, you can actually look it up you do a Google search and you say, bracket for 74 teams. It looks all funny because they put them in weird places, but it ends up being 73 matches. Yeah. So it's just the pattern, good pattern one, this one. Okay. All right. Let's look at the next one. A coin is tossed 6 times. Okay, so we're going to do a little lesson. We're going to do some work on probability a little bit later in the year. But this is a good intro to that as far as figuring some stuff out, kind of doing it by trial and error, or just counting things up. Coin is tossed 6 times. Okay. How many ways can it come up? 5 times heads 5 times and tails once. Somebody give me one. Let's just try the first way. Give me a head or a tail. Heads. Okay. Comes up heads once. We're going to do that 5 times. Couldn't I do heads, 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 tails? Is that one way to do it? Okay. What's another way to do it? Okay, we could do that. Let's try to make it a pattern, right? Because if you can do a pattern, then you can make sure to get all of them in there. If you did tails here, I guess you could do that, but that might mess this one. You try to flip as few as you can. In other words, let's try this. What if we did heads, 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 tails, heads? That's another one. What would I do next? Whoops. Tails, heads, tails. And then the same thing, heads, heads, tails, heads, heads, heads. And then heads, tails, heads, 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 heads. And then tails, heads, 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 heads. Are there any other solutions? Did we get them all? Yeah, you're sure we got them all? Yeah, we can look and we can go try to come up with another one that we didn't get. Well, we did. We got all of them where there's only one tail and 5 different heads. right? 2, 3, 4, 5, 6. There's your answer. So this is where you, what we call, enumerate all the different solutions. You write out all the solutions. You can't do that very easily if you said, let's flip a coin 1,000 times, right? You're not going to do that. And let's say there's 26 heads and 900 and whatever, 74 tails or whatever, right? So that would be bad. You would not want to do all those out unless you're Rain Man or something, right? You just couldn't do it. You want to actually figure out a way, which we'll do in probability later. OK. Number 12. Place the digits 1 through 9 in a 3 by 3 square such that each row, column, and diagonal add up to the same total. The nice thing about this one is they give you a few answers, so you can just kind of guess and check like each little one to see if it's right. But if they did it this way, 1, 2, 3, 4, 5, 6. Any Sudoku fans in here? Yeah. This is kind of a similar sort of thing, except that you have to add things together. 3, 9, 2, and 6. Okay. There are ways to figure this out. I think it's called a magic square. I think that might be what it's called, a magic square. What we're trying to do is we're only supposed to use 1 through 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. And we've already used 3, and we've already used 9, and we've already used 2, and we've already used 6. Okay? And what you can do is you can start to plug numbers in here and see if it works out. The best way to do is to look at the answers here and actually say which one works, right? There are other ways to do it, though. There's definitely some formulaic ways to do it if we wanted to. Let's see. If we put, let's see. I don't even know where we might start on this one. This one might be one where you just kind of guess and check until you get it. Tell you the truth. What's that? If we put, let's say we put the, I don't know, the 4 there. What does this add up to? 13. Okay. Well, this, sorry, 15. Thank you. 15. Yeah. And then what would we have to put here? 8. 15. And then now we've got rid of 8, and we've gotten rid of 4. OK. What would we have to put here? 1. That's good. So far, so good. What would we have to put here? 10. The 5, maybe? Hey, this might work out. And then the 7. Okay. It just happened that I guess it just happened that I chose wisely. If we'd chosen a different number, we might have gotten a certain way, but then we would have had to use a number we already tried, or we already used, and it wouldn't have worked so well. Okay. Good. All right. This next one I like because, again, it's like, can you count up properly? The next one's like the kinds of questions they give you when they want to know, like, for IQ tests and stuff, right? You have a box like this, and it's got 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. It's a 5 by 5 box. Find the number of squares in the box. In other words, anything that's square counts. So does this count? The whole thing?
Yeah.
Sure. Does this count? Yeah, that counts. Does a 3 by 3 count? And then the other 3 by 3, but you can't overlap, right? You can only count the ones that exist. So what's a method we might use to do this? Any ideas? Elimination? That's not a bad idea. How would you start eliminating things?
A very long time.
I bet we can do it faster than you think. Okay? Should we start with the little squares first or the big one? Start with the small ones? OK. How many small boxes are there? 25. So let's write those down. There's at least 25. And these are the 1 by 1. OK? How many? Let's do the easy. Let's do the next one that's easy. 5 by 5. How many of those are there? 1. How about the? Want to do the 4 by 4? We'll go down if you want, sure. 4 by 4. Okay. 1, 2, 3, 4. 1, 2, 3, 1, 2, 3, 4. It's like this one here. Okay. So there's 1. How would we find the next one, 4 by 4? I would say pick a direction and go that way. Do you want to go right or down? Down? Okay. So there's 1. And if we move the whole thing down, how many total in the down direction would we have? 2 total, right? 2 down, we'll say. If now we can't go down any farther, so let's go back to where we were and go right. There's 1 here. And that's another one. So there's another one there. So it's a third one there. We already counted that first one. And then if we went down and went over, there's another one. So how many total are there? 4? Do it this way. Put a little table. OK. All right. Now let's do the 3 by 3, because we got to do all of them, right? So 1, 2, 3, 1, 2, 3. All right. Same thing, right? 1, 2, 3. Right? 1, 2, 3. So there's 6. And then you kind of go 1, 2, 3 that way, and 1, 2, 3 that way, for a total of, is it 12? I think it's 9, actually. 1, 2, 3. Right? You can go down 1, 4, oops, 5, 6, 7, 8, 9. 2 by 2. Anybody notice a pattern here? 1, 4, 9, something, 25? It is kind of an inverse square relationship. What's 1 squared? What's 2 squared? What's 3 squared? What's 5 squared? What's 4 squared? I bet that's it. Now if we try to do it, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. For a total of 55. So you can do it that way. That's kind of that's certainly the longish way to do it, but you can do it that way. OK. Problem solving and exponents, what we covered tonight. I'm not going to make you guys do the other sheets, but I did hand out, which we did 2 of the 3 at this point. OK, the other one that we still really haven't gotten to is the word problems one that I know a bunch of you guys have worked on. Yeah, I don't have it up here, but it's the basic word problems on the stuff we did the other day. So it's kind of from your homework 1. Tomorrow we have class same time. Next week, I want to tell you tonight and tomorrow night. Next Saturday we have our first test. I will tell you again. Next Saturday we have first test. I forget how long I said it is. Like 20 or 30 minutes. 30 minutes maybe. I will time it only so that we can get to stuff back to learning stuff. But if you don't finish in the time, you can stay after class and finish it. Okay, I will not make it a timed exam in that sense. I want you to be able to do the problems, not worry about taking the time on them. Questions? All right. What's that? Is there a shorter way? What's the shorter way? Oh, the shorter way here is to notice that for each one of these things, you get a power inverse or square relationship there. And then you go, so for 6 by 6, it'd be the same. Well, we might have a different relationship, but we would do the same idea and go, oh, I see a pattern. Pattern matching is probably where you go. Yeah. OK, I'll see you guys tomorrow. If you had questions about your homework, come on up and we'll chat.